So what's the link between limit points and limits of sequences? A nice following theorem will highlight. The point C and R is a limit point of a set A if and only if there's a sequence of points in A. I'm calling it xn here, but it might be smart to call it an to remind us that the sequence is entirely contained in A, with all of the points being different from C every n, such that the limit of the sequence is C. And so we would be able to show, for instance, in the previous example, that 0 is the only limit point of A, because the only sequences of points in A which converge to anything have to converge to 0. There's no other place to go. This is an if and only if statement, so we have two directions to prove. To simplify the notation, and again to remind us that these sequences have to reside in A, I'm going to write an instead of, but it doesn't matter what we call it. This is just to make it easier to go through the proof. Let's start by assuming that C is a limit point of A. By definition, what this means is that every neighborhood of C contains a point of A other than C. In particular, the neighborhood of radius 1 over n around C contains at least one point an in A. Not contain. It might contain more than one, but it at least contains one. So pick one of those and name it an. Remember, it's not just that it contains a point in A, it is not equal to the point C. And this is going to be true for every choice of n, because every n gives rise to a different delta, 1 over n. Because it's a limit point, every neighborhood around C contains a point other than C in A. Particularly true for a sequence of neighborhoods, 1 over n. Alright, so now this is what we've worked with, given that we had a limit point. Let's try to prove what it is that we want to prove, that there's a sequence of points, each one of which is different from C, that converges to C. So we need to prove we have a convergent sequence. We have a candidate for the limit. We use the definition. Let epsilon be greater than 0. By the Archimedean property, there's going to be some integer n epsilon such that 1 over n epsilon is strictly smaller than epsilon. Right? Typically speaking, here we would say there's an integer n epsilon which is greater than 1 over epsilon, but we've done this often enough that you know where this is going. So I'm skipping the intermediate step. Then whenever n is greater than this n epsilon, which is guaranteed by the Archimedean property, we have distance between an and C is going to be smaller than 1 over n, right? This is by choice of an. We are picking a point an which is within 1 over n of the point C. And so the distance between an and C is always going to be smaller than or equal to 1 over n. Well, strictly smaller, but also smaller than equal. And because n is greater than n epsilon, this is going to be smaller than 1 over n epsilon, which is smaller. So we've shown that given any epsilon, we can find index, integer, after which all of the points are closer to C than epsilon. We conclude that the ANs converge to C. And I remind you that by construction, this AN is not equal to C, so none of the AN are equal to C. So here we've shown one direction of the if and only if statement. Now we'll go the other way. Let's assume that we have a sequence in A such that AN is different from C for all n, and the ANs converge to C. We want to show that every neighborhood around the point C will contain points in A other than C. So pick an arbitrary neighborhood. By definition, because you have convergent sequence, there exists some n integer delta such that the difference between an and C is smaller than delta whenever n is greater than n delta, and also by assumption, we've assumed that the ANs are not equal to C, the difference is greater than 0. Now you might find this confusing because usually this line here would be written with an n epsilon instead of a n delta. But what the definition of convergence of a limit tells us really is that if you give me any positive quantity, any distance between a limit candidate and the values of the sequences, you can find a point after which all of the terms will be within that distance. Now, usually we call that distance epsilon, but that's just the convention. We could also call it delta, right? So this is just rewriting the statement above. There's a sequence of terms which are not equal to C, which converge to C. What this means, this line here, that AN belongs to the neighborhood of radius delta around C for every n greater than n delta, and that AN not equal to C for every n greater than n delta. We've picked an arbitrary neighborhood, an arbitrary interval around C, and we've shown, because there was a sequence AN which converged to C, that there is going to be at least one point different from C in the set A and in the neighborhood, and the point which is here. And so this intersection is not empty, and it contains a point which is different from C. That's going to contain infinitely many such points, but it contains at least one, no matter which delta you pick. And you conclude from this, C is a limit point. Any limit point of a set A, in fact, the limit of a sequence of points in A. So if we want to find limit points, we just need to look at sequences and see what they converge to. We'll do an example here. Let A be the set of rational numbers in the interval 0, 1. What are the limit points of A? Let's try to think about this intuitively before we try to answer the question. If you pick sequences of rational numbers in 0, what can they converge to? Give me an example here. The following sequence, what would it converge to? Well, these are all rational numbers. We see that they converge to another rational number, 1 over 3. So it certainly would seem as though rational numbers would be limit points. What about irrational numbers? If you look at the number pi over 4, this is between 0 and 1. It's definitely not rational. It has a decimal expansion. If I look at the sequence where I just keep on adding an extra digit in the decimal expansion, this is going to converge to pi over 4. Now you might say, well, hang on, this is not a rational number. It's not going to, yeah, we don't care about convergence in A here, we care about convergence in R, right? The sequences in A might very well converge to points not in A. So irrational numbers look as though you could converge to them. Rational numbers that have an infinite, never-ending decimal expansion, it looks like you can converge to them. The one place where it might be problematic is if you're working with rational numbers that have a terminating decimal expansion. Because, you know, if you look at the 1 over 8, which we know is 0.125. If we try to build a sequence this way, we'd say I'm going to start with 0.1, then I'll go to 0.12, then 0.125, then I have to sort of keep on repeating 0.125 in order to converge to 1 over 8. But now each of these terms here is exactly equal to 1 over 8, and we said that we're interested in sequences where none of the terms are equal to the limit, and that's not such a sequence. But you do have a way out. I mean, you can basically write 0.125 as 0.124999999 indefinitely. And if you look at a sequence now made up of adding one extra digit in the decimal expansion, you will be converging to 1 over 8. You don't have to worry about any of the terms being equal to the actual, the limit. So it definitely looks as though, based on that, every point in the interval 0, 1 should be a limit point of A. Not super surprising because Q, the set of rationals, is dense in R. This is what we think should be the answer. Let's see if we can actually demonstrate this is indeed the case. And what I've just done here, before we start the proof, or before we start to solve the problem officially, that's something you have to do all the time. There is no way that you, as somebody who is seeing a statement, will automatically see what the answer should be, and then you'll start writing an analytical proof. You have to doodle around to think about what might happen, to try out specific cases, to get a sense for what it is that you're trying to prove. When we present proofs to you, they're often proofs that have been distilled over 300 years. Like, the proof usually makes sense if you stop to think about it, and if you understand the definitions, of course, that's crucial, right? The proof usually makes sense, but this isn't how we think about real analysis. The proof is the final version of the work that you have done. Now, any convergent sequence, I'll specify non-constant here. Any convergent sequence in A lies entirely in the interval 0, 1. So any limit point must be 0, 1. We're working with a closed interval here. And what we're saying is that AN for convergent sequences will be between 0 and 1. So if there is going to be convergence to some number C, the number C has to be between 0 and 1. It's one of the results you've seen about sequences. If instead of working with a closed interval, we were working with the open interval, well, if you had a convergent sequence, something that converges to C, you would actually conclude exactly the same thing as what you're concluding here. The limit has to be between 0 and 1, including potentially 0 and 1. According to our previous theorem, we are interested in sequences of rational numbers 0, 1. And these sequences, if they converge, their limits will be the limit point of the set A. Now we know that the sequences 1 over n and 1 minus 1 over n are in A. These are sequences of rational numbers that lie entirely within the interval 0, 1. We know that 1 over n converges to 0, that 1 minus 1 over n converges to 1, and we conclude here that 0 and 1 are limit points. Okay. Now let's pick some rational number r, which is contained in the open interval 0, 1. Set eta to be the minimum of the following quantity, r, 1 minus r. In this example, eta would be this quantity, because r, at least the way I've drawn it, is above 1/2. Then eta is a positive number, and 1 over eta is also positive. You use the Archimedean property. You can find integer m such that m is greater than 1 over eta. And so r minus eta, that's going to be greater than or equal to 0 by how you've picked this eta here. And that's going to be smaller than r minus 1 over m, right terms here, which by definition has to be smaller than r plus 1 over m. 1 over m is a positive quantity. And this, again, this little bit here, should be less than r plus eta is less than 1. This is true because if eta is equal to r, r is smaller than 1/2. And if eta is equal to 1 minus r, then r is greater than or equal to. So in particular, r minus 1 over n is going to be greater than 0, smaller than r plus 1 over n, smaller than 1 for every n which is greater than choice of m. Now you use the density theorem for the rationals. You can find some number an which is not going to be equal to r, such that r minus 1 over n is going to be smaller than an, which will be smaller than r plus 1 over a, right? R minus 1 over n, that's a rational number. R plus 1 over n, that's a rational number. no matter what choice of n you've picked. So you can find some number in A is not equal to R, is sandwiched or squeezed by these two things. This is true for n. What we've done here is we've built a sequence AN, where every term is different from R. Now this sequence converges to R, right, by the squeeze theorem. Is there anything about what we did here that was specific to R being irrational? No. R could have been a real number, just anything in the interval 0, 1. Doesn't have to be rational or irrational. The same argument holds. So what you would get out of this is that if you pick any real number in 0, 1, you can find a sequence of rational numbers such that AN is not equal to R. Well, if R is irrational, then you know for a fact that the sequence is not equal to R, but if it was rational, you can also pick one with values which are not equal to R, with AN converging to R. So R is a limit point. The set A. Together with the points 0 and 1, which we had precedently shown were limit points, we get that the full interval 0, 1 of the rationals contains, in a sense, limit points fill the holes in your set.